a 70-ton Titan AVLB dropped its bridge into a river, taking the tank with it. The crew survived. The bridge did not. That single failure in 2018 cost the British Army over £2 million and exposed a brutal truth about military engineering. The bridge meant to carry an army into battle can become its own graveyard. Armored bridge layers are a paradox on tracks, a tank chassis hauling a folding steel roadway designed to unfold in 3 minutes under fire, spanning a 40-meter gap while artillery shells crater the ground. The math is unforgiving. A 60-ton main battle tank rolling across a scissor bridge exerts dynamic loads that can snap welds, buckle hydraulic rams, or simply tip the entire contraption sideways into a ravine. The crew sits in a steel box, watching the alignment through periscopes, knowing that a miscalculation of 6 inches means the bridge misses the far bank. What happens when the ground gives way beneath your own launch vehicle? What does it feel like to be the commander of a column of tanks, watching your only bridge crumple under the weight of your lead vehicle, leaving the entire battalion stranded on the wrong side of a river with the enemy closing in? Today, 8 armored bridge layers that collapsed, folded, or sank before they ever saw the enemy. Before we start, tell me in the comments where you're watching from and subscribe so you don't miss which failure takes the #1 spot. Valentine Bridge Layer. In 1942, British engineers faced a brutal problem in North Africa. The Valentine tank was reliable, but it could not cross the deep anti-tank ditches and wadis carved into the desert. The solution was to bolt a 34-foot-long Class 30 scissors bridge onto the chassis. The bridge, weighing over 2.5 tons, sat folded on the tank's back, its 2 halves hinged together like a giant metal insect. The mechanism was simple and brutal. A hydraulic ram pushed the folded bridge up and forward, its sections unfolding under gravity until they locked straight, spanning a 60-foot gap. The tank then drove through the bridge supports, detached itself, and the bridge was down. On paper, it was a 10-minute operation. In reality, the physics of the launch were a slow-motion catastrophe. The entire mass of the bridge, pivoting on a single point, shifted the vehicle's center of gravity violently forward and up. The Valentine's compact 16-ton hull was not designed for this top-heavy strain. The suspension, a system of 3 small road wheels per bogie, would compress unevenly, tilting the tank onto its nose. In soft sand, the forward momentum of the unfolding bridge could simply shove the tank backward, ruining the launch. The hydraulic pump, driven by the tank's AEC petrol engine, was underpowered for the task. It groaned under the load, lifting the bridge with agonizing slowness. A crew, exposed and working hand pumps, needed up to 20 minutes to complete the cycle. In combat, this was a death sentence. The crew was entirely unprotected, standing on the hull, while enemy machine gunners and mortar teams had a stationary, silhouetted target. The bridge itself was a rigid, brittle structure. It had no give. When a tank crossed, the entire stress concentrated on the locking pins. They sheared. Bridges collapsed under their own armor. Production stopped at fewer than 200 units. The idea was sound, but the chassis was too light, the hydraulics too weak, and the crew too exposed. A bridge that takes 20 minutes to launch under fire is not a bridge, it's a coffin. But the Soviet solution to the same problem was even more brutally direct, trading finesse for raw, armored mass that brought its own set of catastrophic problems. MTU-55. The year is 1962, and Czechoslovak engineers at ZTS Martin begin a project to keep the Warsaw Pact's armored columns moving across the rivers and anti-tank ditches of a future European battlefield. The solution is a bridge layer built on the proven T-55A chassis. The turret is removed. In its place sits a massive scissors bridge, 18 meters long, capable of supporting 50 tons. Production starts in 1969, and over 1,762 units roll out by 1983. The concept is sound, but the execution harbors a critical physical flaw. The launching mechanism is a hydraulic nightmare that demands the tank's engine to be running at high RPMs just to generate enough pressure. The bridge unfolds like a giant pair of scissors, swinging forward and down. The entire sequence relies on a bank of high-pressure piston pumps and a maze of mechanical levers. In theory, the crew can do this from inside, hatches closed. In practice, the system is a glutton for power. When the ground is soft, the idling tank sinks. When the driver throttles up to feed the hydraulics, the tracks churn mud, the chassis digs in, and the entire vehicle becomes an immobile steel island, half-deployed bridge and all. The very act of trying to launch the bridge often stranded the machine before the first tank could cross. The manual backup is no salvation. A crewman has to climb out and wrestle with uncooperative levers while exposed to artillery and small arms fire. The bridge itself is robust, but the delivery system is a temperamental beast that picks the worst possible moment to fail. The Soviet Army accepted it as the MTU-55, and it served for decades. A tool that worked brilliantly on a parade ground and became a liability in the mud. But the Americans had their own bridging fiasco, and their solution involved a hydraulic system so complex that a single leak could freeze an entire advance. M48 AVLB. In the late 1950s, the U.S. Army needed a way to get its new 60-ton M60 tanks across rivers without waiting for combat engineers. The solution was to take the hull of an M48 Patton, rip off the turret, and bolt on a 63-foot aluminum scissors bridge. The bridge launched through a massive hydraulic system. A double-acting cylinder pushed a yoke. The yoke shoved a crank, and the crank unfolded the two halves of the bridge straight out over the gap. The entire launch was supposed to take under 3 minutes. The problem was the hydraulics. The system ran on a volatile, flammable hydraulic fluid pressurized to over 2,000 pounds per square inch. A single leak in a high-pressure line turned the launch into a catastrophe. A pinhole spray of pressurized oil hitting a hot engine manifold would flash ignite. The bridge, halfway deployed and weighing 14 tons, would freeze in midair. The crew had no way to retract it manually. They were trapped inside a burning vehicle with a bridge stuck to its face, blocking the driver's hatch. Maintenance was a nightmare. The hydraulic pump was driven by a power takeoff from the main engine, buried under armor plate. To replace a failed seal, mechanics had to pull the entire power pack. In the field, this was rarely done. Crews simply hoped the system would not fail during a launch. It often did. The Army kept the AVLB in service for decades because there was nothing better, but the sight of a frozen, half-open bridge on a burning hull became a quiet symbol of a machine that could strand an entire armored column before a single shot was fired. But at least the American bridge was built on a tank chassis. The next machine took a different approach, bolting a bridge onto a truck and hoping for the best. Type 84 AVLB. Entering service with the People's Liberation Army in the mid-1980s, this truck-launched bridge system was a straightforward concept, a heavy folding span mounted on a modified 6x6 chassis, designed to be driven to a gap, deployed in minutes, and then crossed by the armored column waiting behind it. The problem was not the deployment speed. The problem was what happened when the tanks actually rolled onto the span. The bridge itself was built from welded aluminum alloy to keep the overall vehicle weight manageable for its truck carrier. Aluminum offers a good strength-to-weight ratio, but it has a lower modulus of elasticity than steel, and it's roughly 1/3. Under a static load, it bends more. Under a dynamic load, like a 52-ton main battle tank clanking across at an angle, it experiences stress cycles that accumulate in the heat-affected zones of the welds. For early production, Type 84 bridges developed microscopic cracks at these joints after repeated crossings. The cracks propagated. The load-bearing capacity degraded from a nominal rating that should have handled a medium tank down to a point where the structure would fail catastrophically under anything heavier than a light armored vehicle. Chinese engineers had based the design on the assumption that the primary customer would be Type 59 and Type 69 tanks, both weighing around 36 tons. But by the late 1980s, the PLA was fielding heavier machines, the Type 80 and the early Type 85, pushing past 40 tons. When these tanks attempted to cross, the bridge groaned, the aluminum deck plates buckled, and in at least 2 documented incidents during exercises, the entire span collapsed into the riverbed with the tank still on it. The crew survived, but the bridge did not. The Army quietly restricted the Type 84 to supporting only infantry fighting vehicles and light trucks, which defeated the entire purpose of an armored bridge layer. The system was not scrapped. It was reworked into a heavier variant with a reinforced steel span, but the original aluminum bridges were quietly withdrawn from frontline units and relegated to training. The failure was not a single dramatic break, but a slow, material-level betrayal. The metal simply could not remember its own strength after enough tanks had asked too much of it. But the next bridge layer took that problem and made it even more personal, because instead of a truck carrying a bridge, it was a tank that had to become the bridge. AMX-13 Poseur de Pont. In 1956, French engineers stretched the chassis of the successful AMX-13 light tank to create a folding bridge layer. The idea was simple: a compact air-portable vehicle that could drop a bridge across canals and ditches for paratroopers. The result was a machine that could barely carry its own bridge, let alone someone else's army. The core problem was the hinge pins. The bridge folded in the middle, and when a vehicle crossed, the entire load concentrated on 2 steel pins at the joint. Those pins were designed for a Jeep, roughly 1.5 tons, but even a lightly loaded truck exceeded that, and the pins sheared. Not gradually, instantly. The bridge snapped in half under the weight, dumping the vehicle into whatever gap it was supposed to cross. The reason was a fundamental mismatch. The AMX-13 chassis was rated for 13 tons, but the bridge and its folding mechanism added another 8, leaving almost no payload capacity. Engineers tried to compensate with thinner, lighter steel, which only made the pins weaker. Then there was the hydraulics. The same fluid circuit powered both the bridge lift and the turret traverse. If the gunner so much as tracked a target, the bridge stopped moving. If the bridge was mid-lift and the turret rotated, pressure dropped and the bridge slammed back onto the hull. In the field, crews had to choose between fighting and bridging. They couldn't do both. The French Army tested the poseur de pont for 2 years, then quietly canceled it. Not a single unit entered service. The folding bridge concept was sound, but the AMX-13 was simply too light to carry it. The military filed the reports and moved on. But the next attempt at a bridge layer would face an even more absurd vulnerability, one that turned battlefield debris into a hard stop. Brückenlegepanzer, West Germany, 1973. The Bundeswehr needed a bridge layer that could keep pace with Leopard 1 tanks. Maschinenbau Kiel took the Leopard 1 chassis, removed the turret, and installed a hydraulic launching system for a 22-meter aluminum bridge. The bridge split into 2 11-meter sections, carried horizontally on the vehicle. Unlike the American M48A VLB, which raised its bridge vertically, the Biber deployed it horizontally. This gave it a much lower silhouette during launch, crucial for survival on a modern battlefield. The problem was the mechanism. To unfold the bridge, a hydraulic ram pushed the 2 sections apart on rails, and they locked together at the center. The rails, the locking pins, and the deployment arms sat fully exposed on the hull. A single close artillery hit, even a near miss, could pepper the area with shell splinters. If shrapnel struck the rails or jammed the sliding mechanism, the bridge would halt mid-deployment. The crew could not retract it under fire. The vehicle became a stationary target, blocking the very obstacle it was supposed to cross. Engineers had assumed the horizontal method would be stealthier, but they overlooked the vulnerability of the exposed mechanics. 105 Biber were built. Italy license-built another 64. The flaw was never fully solved. Germany replaced the Biber with the Leg 1 in the 2000s. 27 Biber were sent to Ukraine. The same risk remains. The Biber's horizontal deployment was smart, but it couldn't withstand the first artillery barrage. Yet the next bridge's launch mechanism was so exposed that a single machine gun burst could sever its control cables entirely. Churchill Bridge Layer, specifically the small box girder assault bridge variant. It entered service in 1942, built on the hull of the Churchill infantry tank. The concept was straightforward. A 30-foot bridge, folded in half and carried on the tank's back, could be launched over a ditch or river without the crew ever leaving armor. The mechanism used a system of pulleys, a winch, and a long exposed cable running from the tank's front to the bridge's forward tip. To deploy, the tank would stop, the crew would engage the winch, and the cable would pull the bridge up and over into position. The problem was not the bridge itself. The problem was that the entire launch sequence depended on a single, unarmored steel cable stretched taut in the open air. In combat, when the tank approached a gap under fire, German machine gunners quickly learned what to look for: a burst of 7.9 2mm rounds across that cable, and it snapped. When the cable parted, the bridge was no longer under control. It could freeze halfway through its arc, leaving a 10-meter steel ramp dangling uselessly over the enemy side of the river. Worse, the tank was now physically tethered to a half-deployed bridge. It could neither complete nor release. The crew could not reverse without dragging the wreckage with them. They could not advance because the bridge blocked their own path. The only option was to bail out under fire and cut the remains free with hand tools. This was not a rare battlefield mishap. It was a predictable, mechanical failure built into the design. The War Office had rushed the Churchill into production with a year's deadline, and the bridge layer inherited that haste. No one had armored the launch cable because no one had tested it under sustained machine gun fire. The engineering assumption was that the tank would deploy the bridge from cover, but the tactical reality was that it had to drive straight up to the gap. The result was a specialist vehicle that turned its own crew into a stationary target chained to a steel trap. Production of the SBG bridge layer continued, but after-action reports from Italy and Normandy made the flaw undeniable. The design was quietly superseded by a hydraulic system that eliminated the cable entirely. But that fix arrived only after men had died trying to cut their own tanks loose. What followed, decades later, would prove that even removing the cable didn't solve the fundamental problem of launching a bridge before it was fully locked. Titan AVLB. The British Army entered the new millennium with a problem. Its chieftain-based bridge layers were aging, and the replacement needed to keep pace with the 70-ton Challenger 2 main battle tank. The answer was the Titan, an armored vehicle-launched bridge built on a Challenger 2 chassis. It carried a massive, hydraulically launched scissors bridge that could span a 26-meter gap. The bridge itself weighed over 12 tons. The engineering logic was sound. A common chassis meant common parts, and the heavy armor allowed it to operate right on the front line. The Titan could deploy its bridge in under 2 minutes, theoretically allowing an armored column to roll over a river or anti-tank ditch without ever stopping. But the bridge's deployment sequence relied on a complex software-controlled hydraulic system. A precise choreography of rams and locking pins had to fire in a strict order. Raise the bridge vertically, unfold the scissors, extend the span, and then lower it onto the far bank. The final lock engages only when the bridge is fully horizontal. During early field trials, a critical software glitch interrupted this sequence. The control system received a false position signal, indicating the bridge was already fully extended and seated. The hydraulics released the locking mechanism early. With nothing holding it, the 12-ton bridge, still folded and hanging in midair, obeyed gravity. It plunged directly into the gap it was meant to cross. The bridge was a write-off. No one was injured, but the sight of the Army's newest combat engineer vehicle dropping its own bridge into a river was a catastrophic embarrassment. The fault was purely digital. A sensor integration error that mistook an intermediate hydraulic pressure spike for a final lock confirmation. The software was patched, and the Titan eventually entered service. But that early collapse exposed a fragile truth about modern military engineering. When the bridge itself becomes a computer peripheral, a single bad line of code can defeat a 62-ton tank. A bridge is only as strong as the doctrine that deploys it. If you enjoyed this video, leave a like and subscribe to the channel. Drop your idea for the next episode in the comments.